Welcome to video 4 of regression analysis. In this video, I'm going to talk about the matrix representation of the linear model. All right, so up to this point, we have been talking about the linear model, the general form where we write y is equals to x beta plus epsilon, where epsilon accounts for the error term, x as the independent variables and y as the dependent variable. In this video, we are going to learn the matrix representation of this linear model. Let's take a real-world example to understand and how we can express a linear model using matrices. We have talked about this example in each and every video. Let's say you have a data set that contains information for an entire class of students. You know their exam scores, how many hours they studied before the exam, whether they had exam anxiety, and how much sleep they got the night before the exam. Here we use the independent variables like study hours, amount of sleep, anxiety levels to explain something about the dependent variable, which is the student's exam score. So if we write the linear model equation for this problem, it would be y is equals to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus epsilon. So if you have the data set with you, you would have information of this sort. You would have information for n number of students from your class and their exam score, number of hours they studied before the exam, amount of sleep, exam anxiety, so on and so forth. So you would have this data set, and based on this information, we have this linear model equation, and now we are interested in the matrix form of this equation. Y is equals to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus epsilon. Perfect. So let's start with the second column over here. So we have this data set given to us, and we'll look at the second column. It is the column that contains the value of the exam score, dependent variable for n students. So we write all the exam scores of n number of students into a column, and this becomes our y matrix, the dependent variable matrix. And that's it for the y matrix. The y matrix has just one column because each student would have just one exam score. One value for the exam score means one column, and then each row represents the exam score of each student. So different rows means different observation. Rows correspond to the observation, column correspond to the value of the dependent variable for each observation. Therefore, y matrix has n rows, which represents the exam score of n number of students, and just one column. So the matrix representation for dependent variable y is pretty easy. Let's look at the matrix representation of the independent variable x. So the x matrix contains the value of all the predictors. So it will definitely have value of all the three independent variables from the data set of this sort. So we have values for the independent variable x1, the number of hours they studied before the x1. So we have the information of n number of students, and this x1 corresponds to one column, and each row corresponds to the number of hours, the study hours of each student. The second column corresponds to the value that second independent variable takes in the data set. And then the third column corresponds to the value the third independent variable takes. So we have three columns corresponding to three independent variables. But let's look at the equation of the linear model closely. We have y is equals to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus epsilon. Here, all the beta 1, beta 2, beta 3 are multiplied with x1, x2, and x3 independent variable respectively. But beta naught is not multiplied with any independent variable. So given this linear model equation, we would have information about x1 independent variable, x2 independent variable, x3 independent variable, the value x1, x2, x3 independent variable takes for n number of observations we would have this information from the data set. And x1, x2, x3, all the independent variables are multiplied with beta 1, beta 2, beta 3 respectively. But in the linear model equation, we have beta naught, and there is a beta naught that is not multiplied with any x. So to handle that in matrix form, we introduce a column of ones in front of the predictor values. So now the X matrix would become a column of ones, which will correspond to the beta naught that is not multiplied with any independent variable, and then the value of all the other independent variables that is present in the data set for n number of observations. So given this equation, y is equals to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus epsilon. Now here the intercept beta naught is not multiplied with any independent variable, but we can think of it like this, that beta naught is multiplied with 1. Beta naught is not multiplied with any independent variable, but beta naught is equals to beta naught times 1. So here we have 3 columns for x1, x2, x3, the value independent variable x1, x2, x3 takes, and in front of that we put a column of 1. So this way even beta naught can be treated like a regular coefficient that multiplies with a value, and in this case just that value is just 1. So X matrix becomes a matrix with 1 columns of ones followed by the columns of independent variable values. So this is how the X matrix would look like. Each row would be one observation and each column would correspond to a predictor, with the first column being all ones because we want beta naught not multiplied with any predictor but multiplied with just 1. Let's look at another matrix, which is the beta matrix. For any given linear model of this form, we write beta matrix as beta naught, beta 1, beta 2, beta 3. So we basically stack all the betas we have in the linear model into a column. Each of these beta corresponds to one column in the X matrix. Look at the X matrix again. So in X matrix, we have a column of ones followed by the values of each independent variable. And since we have added a column of ones in X for the intercept, we include beta naught at the top of our beta matrix. The reason being because we want beta naught not multiplied with any X. And then we have beta 1 for x1, beta 2 for x2, and beta 3 for x3. So the beta matrix has one row for each predictor, including the intercept, and just one column because each predictor has only one coefficient. Remember, no model is perfect. We always have some sort of randomness or noise in our model. And that randomness, we call it error term, epsilon. And the matrix representation of the error term would look like E1, E2, E3, so on and so forth till En. Let's try to understand why would we have this matrix representation for the error term. In this particular problem, we have x1 that represents study hours, x2 exam anxiety, x3 amount of sleep. And these factors, these independent variables, definitely affect the exam scores. But there might be other independent variables, there might be other factors actually we have no information about, such as the number of hours students spent using social media, number of assignments completed before the exam. All these other factors might influence the exam score, but we have no information about that. So in each observation, the actual exam score would differ from what the model predicts due to those unobserved factors. So in each value in the epsilon matrix corresponds to one observation, that is one student, and reflects how much their exam score would differ from what the model predicts due to unobserved factors. We are talking about this problem where we have the data set that contains the information about the student's exam scores, study hours, exam anxiety, amount of sleep, so on and so forth. And we have seen the matrix representation of the dependent variable y, x1, x2, x3 betas and epsilon separately. But if we were to write it all together, the final matrix form of this linear model would be value independent variable takes for n number of observation for n students. Each observation corresponds to the exam score of n different students, and then the matrix representation of x matrix multiplied with the beta matrix, the coefficient matrix, plus the error term, which is the matrix representation of epsilon. Let's generalize this. Say we have p predictors and n observations in the model. The matrix form in general for the linear model would look like this. Since we have n observation, we would have n different values of the independent variable. We have p predictors, so definitely we would have x1, x2, x3, so on and so forth. That would represent the p columns of the x matrix, but then we have a beta naught. In order to take care of this beta naught, we would add a column of ones followed by the values all the other p independent variable takes. And that is multiplied with the coefficient matrix, the beta matrix. Here we have p plus 1 number of betas, p betas, because we have p independent variables multiplied with p betas. And then we have an additional beta naught, which is not multiplied with any x, treated as an intercept. So we have a beta matrix that consists of beta naught, beta 1, beta 2, so on and so forth till beta p. And then we would have a matrix for error term. X matrix, total number of rows is n, because each row in the matrix X again represents one observation, and each column in X represents one of the independent variables. The very first column is made of all ones. That's added to account for the intercept term. So the total number of columns in the X matrix is p plus 1. Now let's understand each row of this matrix. If we zoom into just one observation, say the first one, the equation would look like, for the first observation y1, it is dependent on beta naught plus beta 1 times x11 plus beta 2 times x12 plus beta 3 times x13, so on and so forth, plus beta p times x1p plus epsilon 1. We know what y1 represents here. We know beta naught, beta 1, beta 2, beta 3, so on and so forth, beta p are the coefficient of the independent variable. But now what exactly is x11? x11 is the value of the first independent variable for the first observation. What is x12? x12 is the value of the second independent variable for the first observation. Remember, in X matrix, the rows represents the observation and the column represents the predictors. So if we look at this entry x12 here, the subscript 1 would be row, 2 would be the predictor. So x12 is basically the value of the second independent variable for the first observation, because rows correspond to the observation. Now if we look at x1p, 1 correspond to the row, p correspond to the predictor. Therefore, x1p is the value of the pth variable, pth independent variable for the first observation. So if we generalize it, and if we look at any ith observation where I could take any value from 1 to n, because we have n number of observation, so any ith observation would look like yi is equals to beta naught plus beta 1 xi1 plus beta 2 xi2, so on and so forth, beta p xip plus ei. Here, yi is the value of the dependent variable for the ith observation. xi1, again, I correspond to the row, 1 correspond to the column, and we know rows represent the observation, column represents the predictors. Therefore, xi1 represents the value of the first independent variable for the ith observation. Similarly, xi2 is the value of the second independent variable for the ith observation. And if we look at xip, xip would be the value of the pth independent variable for the ith observation. Perfect. So this is how we write the matrix representation of any given linear model. Now, since we know the matrix representation, there is one more important thing we should know about is the dimension of each matrices we have discussed. The dimension of any given matrix is defined by the number of rows times number of columns. So given P predictors and N observations in the linear model, this is how we write the matrix representation of that linear model in general. Now, if we look at the dimension of the Y matrix, we have the value of the dependent variable for each observation. Rows correspond to the observation, so we have n observation, n different rows, and we just have one column. And thus, the dimension of Y matrix is n cross 1. Let's look at the dimension of X matrix. We have added a column of ones in X for the intercept, followed by the values of all the other independent variable. Therefore, we have n observation, n rows, and then we have p columns for p independent variable plus one column we have for intercept. So in total we have p plus one number of columns, and the dimension of X matrix is n rows cross p plus 1 number of columns. Dimension of X is n cross p plus 1. Now to write the dimension of beta, we need to understand the matrix, the coefficient matrix beta. Here we have p betas because of those p independent variables plus an additional beta naught. And thus the dimension of beta consists of p plus 1 rows and just one column, because at the end we have stacked all those betas into one column. And the dimension of error matrix would be n cross 1 because we have error corresponding to each observation, and thus we end up getting n rows for each EI error term with respect to each observation cross one column. We just have one column over here. So the dimension of the error matrix is n cross 1.